Welcome to our lesson on circle theorems. In this particular lesson, we are looking at the last three theorems in this series. We have so far covered 7 theorems. Theorem number 1 was talking about perpendicular to a chord which is drawn in the circle bisects the chord. Then theorem number 2, we said if you have two chords that are drawn inside the circle, equidistant from the center of the circle, then those two chords will be equal in length. Then those first two theorems are based on the chord. So we moved on to look at the next set of 3 theorems that are based on the angles in a circle. And that is theorem number 3, which states that the angle at the center of the circle will be twice the angle which is at the circumference if these two angles are subtended on the same chord or by the same arc. And then theorem number 4, we said that angles that are in the same segment are equal if they are on the same chord, or angles in the same segment because they're coming from the same arc, they are all equal. And theorem number 5 is that if the chord is a diameter, which means we have a semicircle, so angles in a semicircle are right angles or 90 degrees. Then we have moved further to look at theorem number 6 and 7 that are based on the cyclic quadrilateral, which we said the cyclic quadrilateral is simply a plane figure, a 4-sided polygon with all its 4 vertices touching the circumference, or the 4 vertices are points on the circumference. So theorem number 6 says that the opposite angles of a cyclic quadrilateral add up to 180. Any two opposite angles, since the quadrilateral has 4 angles inside, any set or any pair of opposite angles will add up to 180. Then the 7th theorem is where we're saying if we extend one side of the cyclic quadrilateral and create an exterior angle, that exterior angle will be equal to the interior opposite angle. So just before we go to our last set of 3 theorems, we'll first look at an example using the theorems we have covered so far. So there's an example here of a diagram A, B, C, D, E, which are points on the circumference, and with that information given. So we want to find the angle ADE, the angle DAE, and the angle BAD. So if we look at ADE, we can try to sketch just that part. We can try to sketch just that part of the diagram. Now there is the circle, just that part of the question. We have A is here, D is here, and E is here. If we look at the diagram the way it is given, we have a chord AD and a chord DE. Then there are 2 angles. One is at the center. We are told this one is 80 degrees as in the question. Then we are told this is equal to that. DE is equal to AE. That is how that question is. Of course, the chord AE is drawn as well. This chord is given. So, but the question is to find ADE. ADE. Okay, ADE is that angle there. Okay, so we can tell that this angle at D, okay, is related to the angle at the center. They are all coming from the same chord AE. Okay, so according to the theorem, theorem number 3 of the theorems based on the angles in a circle, we said the angle at the center is twice the angle at the circumference, which means angle AOE, angle AOE is two times the angle at the circumference, ADE. Okay, the angle at the center is 2 times the angle at the circumference. So because AOE is 80 degrees, it means we can find the angle ADE. It means the angle at the circumference is half. It's half of the angle at the center. So to find our AD, we divide by the coefficient 2, which means ADE is 40 degrees. Okay, so just from that sketch, we know that will be what? That will be 40 degrees. So that is how we can interpret that from theorem number 3. Okay, from theorem number 3. Then the next question says we find DAE. So from the same sketch, D is here, A is here, sorry, this is E here, this is A is here, and E is here. So if we look at this information, the diagram says DE and DA are equal. Okay, there are markings on DE and DA suggesting that DEA is an isosceles triangle. So for an isosceles triangle, we know that these two angles are equal if it is an isosceles triangle. Okay, so knowing that this is 40, the angle at D is 40. Okay, we can find DAE. We can find DAE because this one is 40. We can find this angle here, DAE is this one here. DAE is this angle here. So we can find DAE because this is an isosceles triangle. So what we do is we'll say DAE is simply 180 because the three angles should add up to 180. So DAE is simply 180 minus the sum of ADE plus DEA. Okay, that is just the interpretation, but of course we know that the angle at E and the angle at A are equal. So we simply get 40 from 180. Sorry, okay, 40 from 180, so that we get 140. Then we say the 140 we divide by 2 because okay, because DAE is equal to DEA. Those two angles of an isosceles triangle are equal. So we have 70 degrees, which means DAE, the angle we are looking for, DAE, sorry, that is a caret there on, I want to put a caret on A, okay. DAE is simply 70 degrees. Okay, then the last part of the question is to find BAD. You can see in the question there. So again, to use the same sketch. Now, when you look at the diagram carefully, you will notice that D, A, B, C, and E is here. Okay. The D, E, A, and B, it's a cyclic quadrilateral. Okay. Of course, can disregard the C there. But if you look at the diagram, D, B, A, E, D, B, A, E, all those 4 points are on the circumference. They are points on the circumference of the circle, which means this DBAE is a cyclic quadrilateral. Okay, so because it's a cyclic quadrilateral, it means the opposite angles, this plus that, is equal to 180. Okay, just like this plus that is also equal to 180, according to the theorem on cyclic quadrilateral. So DEA, we have said DEA is 70 degrees. Okay, which means the angle we are looking for, BAD, BAD can be found by interpreting the related angles that are here. Okay, first of all, there is C here, which is like that. Okay, there is an angle at C which is given to us as 20 degrees. Okay, now the angle at C, which is 20 degrees in the question, that 20 degrees there at C, it's in the same segment as the angle at D coming from AB. Okay, so this 20 degrees which is here, it is equal to the 20 degrees at C the 20 degrees at C coming from AB is equal to the 20 degrees at D coming from AB. Okay, is equal to the angle coming from AB but at D, that angle there. So this is also 20. All right, so in short, we have let me just quickly resketch. We have something like this. We have a triangle where this is 20, this is 20 because it is in the same segment as the angle at C. Okay, C is here, A is here, and B is here. Okay, so because the angle at C is 20, it means even the angle at D is also 20. Now, this angle at B, this one, if you look at it carefully, that angle is inside the cyclic quadrilateral. The angle at B is inside the cyclic quadrilateral. So we'll say this angle here is opposite to that 70 degrees, okay? Which means if this angle at E is 70, this one, which is opposite that one, okay, if this is 70, then the angle here is 110, okay? We'll say 180 minus 70, we'll get 110. So the angle we are looking for, is BAD. BAD is this angle here, okay? So we get this angle by simply adding the 20 and the 110 and subtracting from 180, because that is a triangle. So we'll have 110 plus 20, which is 130. Then we get 180 less 130, which means our angle is 50 degrees. Okay, BAD is 50 degrees. So that's how we can solve those questions based on the theorems that we have covered so far. So we can quickly run through the last three theorems based on the tangent to a circle. Then we'll look at another set of examples in our next lesson. So for now, let's quickly look at the theorems that are based on the tangent. There are three theorems, the last set of three theorems based on the tangent to a circle. Now, if this is a circle and we draw a straight line outside the circle so that it touches the circle only at one point, okay? If this is a circle and we draw a straight line that will touch the circle only at one point, then we can call that line a tangent. So a tangent is any linear function or a straight line that tangent line will touch the circle only at one point, okay? So theorem number 8 on the circle theorems. Theorem number 8 says if we draw a radius and that radius is perpendicular to the tangent, if that radius touches the tangent at the point of contact, then it will be perpendicular, okay? Radius of a circle, the radius of a circle is perpendicular at point of contact with the tangent, okay? Perpendicular, which means it's at 90 degrees perpendicular. The radius is perpendicular at the point where the tangent touches the circle. At the point, the radius is perpendicular at the point where tangent touches the circle. Okay, that is theorem number 8. So because this tangent is only touching the circle at one point, if we draw a radius, meaning if this is the center of the circle, for example, the radius at the point where this tangent touches the circle, this radius will touch the tangent at 90 degrees. Okay, that is the theorem. The radius is perpendicular at the point where the tangent touches the circle. So just this particular radius will be at 90 degrees to the tangent. Okay, that is theorem number 8. Then theorem number 9 states that two tangents that are meeting at an external point, two tangents intersecting at an external point are equal in length. Meeting at external point, they are equal in length from the point of contact to the point of their contact with the circle to the point where they are intersecting. Okay, are equal in length. That is theorem number 9. What this theorem says is, if we draw another tangent and allow them to meet at an external point, okay, if we have let's say a point Q where there is another tangent, and then maybe they meet at T or at point Z at an external point, okay, it means these two tangents will be equal. Remember, here there is also a 90 degrees here. If we draw another radius OQ, it means this one is equal, and OQ, this is O, okay, this is O, the center. So OP is equal to OQ because they are both radii, and we are saying the tangents also from the point of contact. So PZ will be equal to QZ. Okay, does this look anything familiar or anything interesting? Yes, this gives us a kite. Usually theorem number 9 gives us the interpretation of a kite, because what we have is a situation where these two shorter sides of the kite, they are the radius of the circle. Then we have the two longer sides of the kite are the two tangents, with these two opposite corners as points of contact with the circle. So we normally employ either the Pythagoras theorem if the question has to do with finding the length of the tangents, or we can interpret the angles inside there like we have done with the other theorems. So, and then the last theorem which deals with the tangent is where we have a chord at the point of contact with the tangent. So if we have a circle and there is a tangent, okay, let's say we have a tangent, and at the point of contact of this tangent with the circle we draw a chord, okay, we have created an angle between the chord and the tangent. So if we say this is let's say point Q, PQ, if this chord is PQ, okay, we have created an exterior angle or an angle here between in this segment here we have created an angle between the chord and the tangent. So if we have any other angle from the same chord PQ, okay, the other side of the same chord, this angle here between the chord and the tangent will be equal to those angles in the other segment. So we call the theorem number 10 as the angle between chord and tangent, the angle between the chord and tangent at the point of contact. Is equal to angle in the alternate segment. Is equal to angle in the alternate segment. Okay, so like we have seen here, by introducing a chord PQ on the tangent, if we have, for example, we say, so we have introduced a chord PQ on the tangent. Let's say the tangent is SPE, that is the tangent at the point P, that's where it is intersecting with it's touching the circle. So the angle we have created, QPE, that angle QPE, which is formed by the chord and the tangent, that angle there, it will be equal to any angle which is in the alternate segment. We can have an angle at A, an angle at B. So those angles at A and B, they will be equal to this angle which is created between the chord and the tangent. That is theorem number 10, and this concludes the 10 theorems that we have on the circle, or circle theorems. So we'll look at some examples in our next lesson.